In this example, we're looking at this block P, which is going to be sliding down a rough angled rod. We know that the coefficient of friction, of kinetic friction between the block and that guide is 0.3. We know that it can drop through a distance d before it hits a spring, and again at that point it makes contact with a spring of stiffness k. And what we want to know is that if this is released from rest at that distance of d along the rod above the spring, what we want to do is find the maximum deflection of the spring. That is the amount of compression we have in that spring when the particle initially comes to rest by the spring before it starts back up the rough guide. Okay, so we're looking again for a change in position with a change in energy. The energy here is going to be the potential energy of gravity and the potential energy of that spring, as well as some work terms. So what I'm going to do is draw a free body diagram of block P. Let's look at the forces that act on that, and with the end result here, figuring out which terms, if any, do work. Well, we have the weight force, mg. mg is going to be at an angle of theta from a normal direction of here. We have a normal force acting in that sense. And since the block is going to be moving down the incline, we have a friction force there, F, to resist that. And also during part of that path, we know we're going to have a spring force which is going to be resisting the motion. So it's going to be acting the same direction as the friction force there of F. So again, since we're looking for change in position with change in energy of that block, we're going to use the work energy equation. Okay, so let's go through the five terms here. T1, since it starts out at rest, initially at rest, T1 is a 0. The potential, we have to make a decision on what we're going to use for our datum. I'm going to arbitrarily choose my datum line to be where the block is when it's released from rest. So with that choice, it's at the datum at the beginning, so V1 is a 0. T2. Well, in general, T2 is going to be 1/2 mv squared. But this is going to be equal to a 0 because we're looking for maximum compression of that spring. In other words, at some for an instant of time, that block is going to be at rest before it starts to come back up. So T2 is also a 0. V2, the potential. V2 is going to be a potential term. It's going to be potential due to a gravity, which is going to be a minus mgh. The negative sign means it's dropping below the datum position. That's the reason for that choice of sign. And then we're going to have potential due to the spring, so that's going to be 1/2 k delta squared. The plus sign is not a choice. This is always plus. Regardless of whether that spring ends up being stretched or compressed, whatever problem that you've got, springs will always add to the potential. So be sure to put a plus there. The only sign you have to think about it is the gravitational part. What's the work? Well, the work term is going to be the integral of the friction force over that path. Well, the friction force is acting up the guide. The block is moving down the guide. So the friction force will have a minus sign because it opposes the motion. The motion is down, the friction force is always up. Integrated over the path. And we know that friction force is going to be mu times n, which is going to be a constant. So that's going to come out on the outside. So it's minus mu k n, and that's delta s, the distance that's traveled there for the block along the guide. So we have all the pieces that go together. We write down the work energy equation of T1 plus V1 plus the work term, 1 to 2. And that's equal to T2 plus V2. One thing that I meant to talk about but failed to do so is for us to really assess of these forces, 1, 2, 3, 4 forces acting on a block, which ones do work. Well, mg we know does work, but it's going to be, as we've seen, we put that in V. Same way with the spring force. That does work, but we're not going to find that in terms of work. Rather, we're going to put that in the potential. We know that the normal force which acts is always perpendicular. So although it's always there, it's putting a force on the block. It's perpendicular to the path, so it doesn't do work. So the only thing we had left, and that's what we put in U, was that friction force. Okay, so then we recall that T1 was a 0. It starts out at rest. V1 was a 0 because we were at the datum position. The work term is mu n times the distance through which the block moves. We saw T2 was a 0 because we're looking at a case where it's at maximum compression. And V2 was minus mgh2 plus 1/2 k delta squared. Okay. So what we're looking for is delta. Kinematics. Recall that the symbol that I used there for delta S is the total distance through which the block slides. We know that that's going to be that distance d that's going to slide before it hits the spring, and that's going to slide an additional distance there of delta through which the spring is compressed. Okay. H, on the other hand, let me draw the picture here. If this total distance is delta S and going from 1 to 2, again, this is delta S. The distance h through which this drops is going to be, we can find that from trig. And let me go back and make sure I've got the right correct angle here. Theta is the angle of the bar measured from the horizontal. So that's going to be this angle here. And that's the same as this one here. So from trig, we can see that h, the height through which it drops, is going to be delta S times sine of the angle. Okay? And that's really all that we need. When we now have all of our kinematics done, we substitute this back into the equation. Again, we're trying to find a delta. So minus mu k in delta S. Delta S is equal to d plus delta. That's there on the left-hand side. Right-hand side is minus mgh. H is sine theta times delta S, which is going to be equal to D plus delta. And that gets added on to 1/2 K delta squared. So what we have here is a single equation in terms of a single unknown. Let me rearrange some of my terms. Let me write this as 1/2 K delta squared. I can put together mu K in, and that's going to be multiplying a delta. We subtract away a minus mg sine theta delta, and what's left here is going to be equal to a mu K in times the distance d, which we know, minus mg sine theta times d. And one thing that I failed to do was find n. Okay, so let's go back up to our FBD here. And I talked about normal and tangential components. So let me draw in, let's say, E sub n here. It's normal to the path. If I sum the forces acting in the direction of n, I'm going to have n minus mg cosine of theta and that's equal to mass times the normal component of acceleration. So again, this here is the summation of forces on the block in the normal direction. We didn't really need to know n in terms of work, but it does come into play because it affects the frictional force, which does do work. Well, since this is a straight path, the normal component of acceleration is a 0, and therefore n is equal to mg cosine of theta. So with n there, we can substitute that in for n there and there. At this point, we know everything except what we're trying to find, and that's a delta. So this becomes a quadratic equation to be solved for delta, and that's what we're looking for here. But again, at this point, we have everything that we need to know. Everything appearing in there except for delta is unknown. Okay, how do we get here? Well, if we go back to our FBD, our goal here was to use the work energy equation because we're looking for change in energy for a change in position. We wrote down T and V initially at rest. I chose my gravitational datum to be at the initial state, so V1 is a 0. T2 is also a 0 because we're looking for maximum compression of the spring. The change in potential, there's going to be a decrease in potential because of the MGH term. It goes down below the datum that I chose. And then there's an increase in potential due to the spring, 1/2 K delta squared. The work term, probably the most important thing on that, is the sign. Friction force opposes the motion. When you do friction dotted with ET for that, you get a minus sign. It opposes the motion, and hence that's how we ended up with a negative sign in front. At that point, it's just a matter of substituting in our 5 terms. We did kinematics to be able to relate the distance that the block slides through, delta S, back to the compression of the spring in addition to that distance d, and we also had to write the height h through which it dropped in terms of delta S, therefore in terms of d and delta. They gave us a quadratic equation to solve for that compression of the spring.